But I'm going to talk, there's no other questions about what we've covered so far with. We have a difference equation, how do we get the Z transform for it, right? And then from that, how do we get the impulse response and vice versa and all that stuff? Are you all good with that? All the homework problems you got? Good. That's what I was mainly concerned about. And we found you get two stages in series, you multiply the transfer functions. Two in parallel, you add the transfer functions. Do you all remember this? Parallel series. Remember H1 of Z, H2 of Z in series, you multiply them to get the output, input-output relationships. Remember that? In parallel. You all remember? I want to make sure, where I'm going with this is I'm going to show you now a further application. It's going to be more real, you might say. Before, if I said if you had some H1 of Z here, and you had an H2 of Z here, and you wanted the input-output relationships if this was X of Z, and this is the output Y of Z, right? And the transform of that would be Y of Z over X of Z is nothing more than H1 of Z times H2 of Z. Y'all remember that, right? Okay. Just getting some blank looks. That's if they're in series, correct, class? If they're in parallel, as such, H1 of Z, H2 of Z. This is the direction of the signal coming into a summer. Then this Y of Z would simply be quantity H1 of Z plus H2 of Z times X of Z. And therefore, the transfer function, the total transfer function, is just going to be H1 of Z plus H2 of Z. You all remember that, right? I'm just doing this, and remember this could have not just two, you could have any number that would just be added as such. Do y'all follow me in this? In this case, if you had any number, that would be multiplicative, right? And you could have any combination of those. Just so you all know this. Now, the other one that we talked about was the feedback thing, where we're going to have some X of Z coming in, and then there'll be a summer. If it's negative feedback, that's the minus. Here, H1 of Z, it's called forward gain. This is Y of Z in the system. Comes back. This is the negative feedback, H2 of Z. And we said that Y over X of Z here was equal to the total transfer function H of Z, and that boiled down to simply H1 of Z over 1 plus H1 of Z times H2 of Z. And we can prove that if you want, but we've done that before. That was negative feedback, right? If it was positive feedback, what happens? That becomes a negative right there, right? Right here it becomes a negative. Y'all follow me on that, class? And that's how you do it. So those are the three basic ways of looking at lump transfer functions as blocks and how they affect the system. I want to get that out of the way. Clear? We've done problems with all of these. Right. Now the next thing. All right. That we're going to do is we're going to be talking about something called windowing. Now, if you think about, like with a radar system that I use, I send out a pulse, and the pulse is coming back at me, being reflected from everything in the world out there. So it's a continuous amount of signal coming back. Sometimes it's going to be almost nothing, but just assume this. Suppose I sent a radar signal out from here into this room and aimed it right there. My return would be a continuous amount of information if I looked at all that, because there's basically obstacles that will scatter back all the way up and down this room. Follow me? What you often have to do in order to do meaningful processing is take chunks of data that is returned, little chunks of data, not the entire data stream. All right? You're going to take portions of that data, because that portion of data will tell me how much information is in the time delayed reflected pulse associated with that. Let me give you an example. You're talking about speed of light delays, right? So I send out a pulse, it's going the speed of light. It hits something. Say that time is, just call it tau 1. Well, the distance it travels is tau 1 times c. Now to return, reflected back, now it's going to be tau 1 times c again for distance, right? But the total travel time would be 2 tau 1. Think about that for a second, right? Now, as that comes back, I want to take a look at the amount of signal between, say, tau 1c, that distance, and some tau 2c, a distance further away. I just want to see how much of the signal returns in that interval. Here's where we use windows. This will give us the ability to figure out what, in fact, is out there at a given range. Does this make sense to you? We want you, you just think about it. You really want to take a look at chunks of time and see how much of the signal returns in those chunks of time. Therefore, you can establish at a certain distance, there's this much electromagnetic information scattered back, and you can get something called the radar cross-section associated with that, if there is a target or if there isn't a target there. Do you follow me on this, class? It's basically like echo return. If you've ever been in an area with mountains at a great distance, you yelled or fired a gun, you hear nothing until the signal comes back from the mountains reflected, right? There's a long time delay associated with the speed of sound. But actually, there's a continual reflection from the ground. It's so minor that your ears don't pick it up. Well, with radar processing, it's the same thing. I send out a signal, there's a continual amount of information coming back at me. I want to find out how much information is in each time window, you might say, so I can figure out where, in fact, the target is. Now, this is really crude, but it should at least pique your interest. This should make sense to you. So we use something called windowing. And I want to do this, I'm going to start with the simplest possible window. First, the window itself. Then we'll take a look at what happens when we get functions in. So when we talk about a window, just label it W of n. This is the next chapter. And we're going to start with something that's called a rectangular window. The value of this is just 1, and it's for n greater than or equal to 0, less than or equal to L minus 1. It could have been n minus 1. We're just going to say there's that many different sample points in this data window. And it's 0 else. So it's 0 else. Now, if we just looked at that itself, and we looked at the spectral transform of it, please follow me on this. We're going to use this window and we're going to multiply function by it in a second, but we first have to take a look at just the response, just what that window looks like in the spectral domain. Follow me, guys? So if you look at this right here, where this is Wn, so it's 1 from 0 to L minus 1, right? I'll do the Z transform and I'll do it the simplest possible way. I'll just say that now my W of Z, the Z transform of this, would be the summation from n equals 0 to really L minus 1 of 1, right, times Z to the minus n. You all agree with that? Because the value in front of there should be x of n, but x of n is just 1 for all those values. Now you'll notice I didn't go to infinity because all values for L minus n greater than L minus 1 are 0. So this is the only meaningful portion of the Z transform. Does that make sense to everybody? Now, based on that, your understanding of the sum like that, that goes to what? Z to the 0, or 1, minus Z to the minus n of L minus 1 plus 1, or minus L, right? Over 1 minus Z. How many remember that sum business here? That was the geometric sum. Do you or not? No? Kind of? I'll put it on the board one more time. Please make sure you get this. This is important. You're going to find out data windows are super, super valuable to understand windowing techniques, especially for people in Wi-Fi, if you're doing anything with Wi-Fi entry. So, in general, the sum business is this. If you have a summation, n equals Q1 to Q2 of any a to the n, like that. And a in this case is 1, or a z, pardon me. Or is z to the minus 1, pardon me. It's going to be equal to a to the Q1 minus a to the Q2 plus 1 over 1 minus a. In this case, the a would be z to the minus 1 to the n. Follow me? So a would be z to the minus 1.
Y'all follow me on this one, class? How this equates? Now, I did this before, but I'm going to do it again. What I'm going to do is go ahead and I'll first factor out z to the minus L over 2 on top, so I have z to the L over 2 minus z to the minus L over 2 over, and then it's going to be z to the minus L, I'm sorry, minus half, pardon me. Z to the minus 1/2 here times the quantity z to the 1/2 minus z to the minus 1/2. Some of you remember me doing this before, don't you? Mm-hmm. Now you know where I'm going with this. My next step is going to be, because I want to take a look at the frequency domain effects. I want to take a look at the actual y of omega, or w of omega here. So now at this point, I let z be equal to e to the j omega. Anytime I do that, now I'm looking at the frequency domain response of the system. You follow me on this, class? Or the frequency domain signature of this windowing operation. And it is, in fact, a filtering operation. So when we take a look at this, we go ahead and we get e to the minus j omega L over 2 over e to the minus j omega over 2. That's only phase here. And then this will turn into e to the j omega L over 2 minus e to the minus j omega L over 2 over e to the j omega over 2 minus e to the minus j omega over 2. Remember what my next step is? This is what? That's a sine. It's actually 2j times the sine of omega L over 2, right? The top part. This part is 2j times the sine of omega over 2, right? The 2j's cancel. So when I'm finally done with this, I get this. I get e to the minus j omega L over 2, only phase, e to the minus j omega over 2. Then I'm left with the sine of omega L over 2 over the sine of omega over 2 here. And this, you might as well just say, is really capital W of omega. Now, we've talked about this before. This is a very simple rectangular window. If you look at this, it has values of 1 from 0 to L minus 1, and it's 0 everywhere. So we're just taking a look at this by itself for a reason. You'll see in a second. Now, what does this look like? Well, we'll plot the magnitude here. We've done it before. If we plot the magnitude of W of omega, right? The thing we notice is this, and I made this argument, if L is large, or if L is, say, I'm just going to use the word large and just leave that kind of nebulous. I'm not going to say greater than 10 or anything, but 10 would probably be an effective number. If you get this, this pretty much looks like a sinc function, because the sine of omega over 2 for small values of omega over 2 look like simply sine, or look like just omega over 2 in radians, and this will look like a sine. So it looks like a sinc waveform is my bottom line on this. Follow me? And I made that point before. And what the magnitude looks like is this. Well, we're going to do something in 1 second. Something like this. And you can see that there's like a taper right there. Follow me? That taper is about proportional to 1 over omega over 2. About that. About that. Now this value, in fact, will be 1. The magnitude of that filter. Here's the key things to note about this. First thing is something called the main beam width. This is called the main, write this down. Now, this is very important. Main beam width. How do I get that main beam width? Think about it just for a second. We did this before. Remember, what I'm showing you right here, this magnitude of omega, I'll literally put it in here. This is really equal to the magnitude of the sine of L omega over 2 over the sine of omega over 2. It's that magnitude. That's our W of omega. Ah. With me? That's the vertical axis. So this is 0. This is omega. Where's this value right there? Remember?
Pi.
How do I get that value? That's when this, the upper sign, is 0, right? Correct, class? Follow my logic on this. So when this function is 0, that's where this is 0. Do y'all agree? Assuming the bottom function doesn't have a corresponding 0. Do you agree, class? All right, well, where is sine 0 at? Sine x is 0 at x equals 0, x equal pi, correct? So you have to set L omega over 2 equal to pi here. Just note that. Right here, I would set L omega over 2 equal to pi, or I'd set omega equal to 2 pi over L. So right here, that's 2 pi over L, and right here, it's minus 2 pi over L. And this would be the main beam width, or it would be 4 pi over L. So I can put that right here. The main beam width is equal to 4 pi over L, where L is the number of samples. That's the first thing you have to notice. Remember, we haven't multiplied any incoming function or reflected function by this window. The only thing we've looked at is the window itself. The z transform of the window, and then we let the z become simply e to the j omega. So we're looking at the frequency domain. Kenny, you were looking hard at this. What don't you see?
I can't see that right.
Which one?
This is 4 pi over L,
Before that,
main beam width.
Oh, okay, width. Got it. Okay.
It's just how wide this main beam is, the main between this 0 and this 0. That's all it is. Now the second thing we have to do, and listen carefully, I want to hear you on this one. How do I figure out what this value is right there? That's 1. What's this value? Think about it logically. Y'all see how that's a relative maximum between first lobe and first null, second null, right? We know the first null is 2 pi over L. Now think about the sign. When is a sign equal to 1 or maximum?
Pi over 2.
It's equal to at pi over 2, right? Pi over 2 would be back here, wouldn't it? So that's, I'm saying the argument. So this, and where, the next one?
3 pi over 2.
Then it's going to be 3 pi over 2, correct? So now, watch this. If we take this and we put, I'm going to do it up here, the sine of 3 pi over 2, sorry, my bad. I have to do this. I have to say this argument, omega L over 2 is equal to 3 pi over 2, or omega L is equal to 3 pi, or omega is 3 pi over L. Do you follow me on this, class? So right here, this point is going to be 3 pi over L. Are you with me? Now what's the value of this function right here? When omega is 3 pi over L. So if we take a look at this, just the value of the function will be the magnitude of sine, right? And we know this is going to be simply 3 pi over 2 here, right? Over the sine of what? Omega is equal to 3 pi over L divided by 2. Correct, class? That's how you evaluate the magnitude of that function. Are you with me, everyone? Now what happens here when we do this? We see that this right here becomes, that's 1, right, over the sine of 3 pi over 2L, divided by L, pardon me. And if that is still small, and it should be, it's equal to approximately 1 over 3 pi over 2 times L. That should be right, didn't it? Let me make sure, this should be 3 pi over 2 divided 3 pi. Omega is 3 pi over L. Omega over 2 is 3 halves pi over L. So L should be up top. And when this is done, what's not coming across here is this value right here. For some reason, this is not. I'm seeing here that this is L over 3 pi over 2, so it's 2L over 3 pi, but then it's definable in terms of L. This actually should be down minus 13.2 dB, always. And I'm trying to see where the problem lies. Let's see, on that one, technically what we have to do, I'm not going to spend much time on this, but let me erase this part just to show you something. I know that should be down 13.2 dB in terms of the magnitude. Let me just get this way. If I take a look at that for a second, if I take a look at the sine of really omega L over 2 divided by the sine of omega over 2, and I take a derivative with respect to omega and set it equal to 0, then I have the derivative first, which would be, with respect to omega, is going to be L over 2 times the cosine of omega L over 2, and it's divided by sine of omega over 2, and then it's going to be plus the first, which is sine of omega L over 2, divided by the derivative of that, which makes this a minus, and then it's going to be 1/2 this becomes
Did you take a second?
1/2, and this is going to be the derivative of this when I have sine of omega over 2 to the minus 1. The derivative of that with respect to omega is minus, and then it's going to be 1 over the sine of omega over 2 squared times the derivative of this, which would bring a 1/2 out front. So that's a minus, and it'd still be the sine of omega over 2 squared there. You have to set that equal to 0. This is not the way I wanted to do it, so I can multiply by sine, get rid of that, make that a singular, then take this to the other side. I'm doing this on the fly kind of quick just to get it done. And when I do that, since I want it equal to, set it equal to 0, then the 2's cancel here, let's see, and I'm not getting what I want quick enough. I'm going to just make it clear to you. This will be down, and I'll put this in the notes, by 13.2 dB. Here's how it comes down to when you take 20 times the log of the value of the magnitude of the sine of L over 2 omega divided by the sine of omega over 2. Magnitude of that at omega here going to 2 pi over L. You're going to end up with, it will be minus 13 dB below the value at the origin. And I'm gonna just leave it that, and there's one other thing I forgot to tell you. That was the problem. This value here, now I see it here, this value here is going to be L. And this value, now that makes sense. This value is going to be L right here would be equal to L over um, three pi, and this would be 2L over 3 pi. So if you take a look at 20 times the log of 2 over 3 pi, you're going to get minus 13.2 dB. Does anybody have a calculator just to prove it for me? Just do this. Take 20 times the log here of 2 over 3 pi. And tell me what that is. I think that's minus 13 dB. I'm sorry, the height of this is not equal to 1, it's actually equal to L. I'm used to seeing that normalized, and this is 13.3 dB below. Did they tell me this number? So let's take this along. Anyone?
I have that one for
What'd you get?
6.42117.
Is that what you get?
I got negative 0.67.
Take 2 over 3 pi,
Okay, hold on, I did times 5.
and then take the log and multiply by 20. You got it?
13.5.
That, yeah, 13.
13.5.
It's going to be somewhere 13.2, 13.5. Just take 2 divided by 3 pi, take the log, and then multiply that number by 20. Minus 30. That's how it comes to, because this is L, and this is going to be L times 2 over 3 pi, and that's down by that factor. So my bottom line on this one is, it's this next bump is 13.2 dB below. Now listen to me careful. This is the one point I want to make with this. I don't care about how far down this one is. But what you would like, if you're doing a filter and you're trying to get a certain number of, a band of frequencies, and you want everything outside of those band of frequencies to be reduced, what you'd like is this one down to maybe minus 40 dB. You would like it not even there. You follow me? You would like to get rid of all these and all these because you would like what's called a notch filter. Something that's a bandpass filter just between here and here. Follow me on that thought. Now, for a rectangular window, you can get it down by 13 dB on the first, that's called a side lobe. It's a lobe really unwanted, first side lobe. But now we're going to take a look and investigate this a little further with windowing. You'll see why I'm doing this, because it gets extremely interesting. We use windows all the time when we collect data and sample data, and then we process that data, and we can tell a lot about what's out there with radars. So now, the next thing is, I take that same windowing operation. I'm just going to call this a W of n. It's going to be rectangular for now. It's equal to 1 for n greater than or equal to 0, less than or equal to L minus 1, and 0 else. Okay? Now, think about this. I send out data with radar. It hits something, an object. It comes back, and I collect data. There's a time delay. Don't worry about the exact, all the exact details of this. But one thing a window will do is, if I starting a window, not say I start a window first at from 0 to L, and then the next one from L plus, or 0 to L minus 1, next one from L to really 2L, follow me? And I start taking these window operations, staggered by the total width of the window, and multiplying the incoming signal. I can take that information and then store it in each one of those windows for further processing. Do you follow me? So let's take a look at what happens with that window if it's being multiplied, or the return signal just for this window is going to be something like a cosine. So follow me. Suppose I have my return signal is going to be cosine of omega naught n times that window, W of n. Remember, it's being multiplied by that window, right? Now, what happens if I have a cosine times any operation, if I go to the Z transform domain? Well, cosine of anything, cosine of omega naught n times x of n, instead of w of n, isn't that just 1/2, right? Times the actual w of z with that added. So then it would be simply the w, and then it would be of omega plus omega naught here. Remember, I'm letting z become e to the j omega naught, or j omega. Are you with me in this class? And then it would be what? Plus omega times omega minus omega naught. Everybody follow me on that? The reason I chose cosine is the cosine waveform is basically the type of waveform you get from reflected signals from radar. Now, if I look at this in the frequency domain, please bear with me. I take the original window I had over here, that sync function, and now I stagger it. I have it at plus and minus omega naught. So this frequency, what this would look like in the frequency domain, out here at omega naught, and at minus omega naught, whatever omega naught is, now I get the original waveform, but it would be staggered, right? It would be shifted. Do y'all follow me? I want you to think about this for a second. Remember, I took a window, I took a picture of something. I just multiplied this window only over a short period of time by an incoming signal that happened to be a cosine waveform. Now, the cosine waveform could have a magnitude here, A, and out here it would have a magnitude A also. But now in the spectral domain, this is what I'd see if I did an FFT and adjusted it. I would see two clear peaks right here. And really the thing I'd see is a peak right here, which tells me that the reflected signal has a certain level of strength, A over 2, and would have a center frequency that I could easily see. Do you follow me? Now that's with a cosine waveform. I want to tell you something. We would like this, we'd like to get rid of all those sidebands. Those are 13.2 dB down, because those sidebands will start giving us a false reading. How many have heard the term Doppler? Doppler. What does Doppler imply? Doppler frequency. Just tell me. Whenever you think of Doppler, think of a race car coming at you. What do you hear? And what happens when it passes? Right? Why? Because the actual wavelength, right, of the sound, when it passes, is elongated because the velocity of an automobile is added to the actual what? Or subtracted from the actual initial frequency that the engine's running. Right, class? Follow me? Now, Doppler frequency shifts when you have things that are moving target indicators. If they're coming at you or towards the actual emitter that they're reflected back to, they increase. There's a Doppler frequency that shifts up. So this would shift up if it was an actual Doppler frequency. If it's hitting something moving at us, do you follow me? It would go up. If it's moving away, it would shift down. But the amount of the shift is very small. So it won't shift up to here. It may only shift to here. Now the only way we can distinguish a shift like that is if we get rid of all these sidebands, or else we won't be able to tell that. That should make sense to you. How many see this right here? So now we explore other windows. And I'm not going to have time to do this, but the first one we do is a triangle window. Let me explain this. This looks like just one. You'll see how this works. When we look at versus n, what I have for this window is simply the value of 1 all the way out to L minus 1 from 0, and this is W of n here, and it's 1. The next window we're going to approach and look at is going to be something called a triangle window, where the actual values of these things are going to just sample a triangle. Follow me? What that triangle window would do is it'll get rid of those, and it'll basically make this thing a bit wider but very sharp, much sharper. Trust me, I'll go through this next time. Then after that, we get something called Hamming windows, Bartlett windows. How many have heard of these before? They're tailor-made, they're weights to this function right here that'll allow you to get rid of the sidebands. Now here's why. Now I told you my thing's radar, right? So I send out a signal without getting into all the details. It goes and it hits things. And I start these windows from 0 to, say, L minus 1. Take that data, store it. Then I start another window from L to 2L. Take all that data I collect, the value of the voltage at all those different points, quantize it and store it, digitize it. Next window, and I get a whole bunch of this data stored. And then I do data processing each one of those data. But the type of window I use will allow me to pre-process the data so I get extremely sharp resolution. And I can tell if there's a target out there moving towards me or moving away from me. I can also tell the relative magnitude or the size of the target. And there's so much more to this, but that sort of gives you a peek at where we're going. I'll do this next time and get into this. We'll give you the quiz now. I know.